Arumugalakshmi. Today we are going to discuss the problems in chapter 9 Kinetic Theory of Gases of class 11 physics. The first problem, a fresh air is composed of nitrogen 78% and oxygen 21%. Find the RMS speed of nitrogen and oxygen at 20 degrees Celsius. So the given data are absolute temperature is given as 20 degrees Celsius. Before we start the problem, we have to convert all units in SI unit. So degree Celsius has to be converted into Kelvin. So we are adding plus 273. So the answer will be 293 Kelvin. And gas constant value R is equal to 8.31 joule per mole per Kelvin. So first we will find the molar mass of nitrogen. The molar mass is given by the atomic mass of nitrogen is 14. So molar mass is 14 into 2 because it has got 2 atoms. So 14 into 2. So the molar mass of nitrogen is 28 gram per mole. Here we have to convert it into kilogram. So the value is 28 into 10 power minus 3 kilogram per mole. Now we can find the RMS speed using the formula Vrms is equal to square root of 3RT divided by molar mass, where R is the gas constant, T is the absolute temperature and M is the molar mass. So substituting the given values and simplifying, we get the Vrms value of nitrogen as 511 meter per second. Now we have to calculate for oxygen. First we will calculate the molar mass of oxygen. The atomic mass is 16. It has got 2 atoms. So 16 into 2 which is equal to 32. So the molar mass of oxygen is 32 gram per mole. So this also we have to convert it into kilogram. So the molar mass is 32 into 10 power minus 3 kilogram per mole. Now we have to find the Vrms using the formula Vrms is equal to square root of 3RT divided by M, where R once again it is a gas constant, T is the absolute temperature and M is the molar mass. So substituting all the values, once again simplifying, we get the answer as 478 meter per second. This is the RMS velocity of oxygen. The next problem, if the RMS speed of methane gas in the Jupiter's atmosphere is 471.8 meter per second, show that the surface temperature of Jupiter is sub-zero, that is less than 0. This we have to prove. So what is given? The RMS speed of methane is given as 471.8 meter per second. The molar mass of methane, we have to find. The formula for methane is CH4. So for carbon the mass is 12. So 12 plus for hydrogen it is 1. It has got 4. So 1 into 4 it is 4. So 4 plus 12 it will be approximately 16. So the molar mass of methane gas is approximately 16, but exact value will be 16.04 gram per mole. This once again we have to convert it into kilogram. So it will be 16.04 into 10 power minus 3 kilogram per mole. Gas constant R value we know that it is 8.31 joule per mole per Kelvin. So now we have to find the temperature. So we use the Vrms formula. Vrms is equal to square root of 3RT divided by M. So we need to find the expression or value of temperature. So we need to reverse this formula for T. So first we are squaring the above equation. So we get Vrms whole square is equal to 3RT divided by M. So from this we will reverse the formula to get an expression for T. After that we will substitute the given values to find the temperature. So T is equal to Vrms the whole square into M divided by 3R. Substituting the values, the temperature is found to be 143 Kelvin. So this you have to convert it into Celsius. So subtracting 273. So the value of temperature is minus 130 degrees Celsius. The next problem. Calculate the temperature at which the RMS velocity of a gas triples its value at STP. STP means standard temperature and pressure. So the standard temperature has to be taken as T1 is equal to 273 Kelvin. So the RMS velocity of the gas, you will have it as V. The new RMS at the temperature T2, that is at STP, is given as 3 times V. So VRMS2 is given as 3V. Now we have to calculate the new temperature. So what we are doing is we are dividing the 2 VRMS, we are dividing, that is VRMS1 divided by VRMS2. We know the formula for VRMS as square root of 3 RT divided by M. So when you divide these two VRMS, the terms which are in common will get cancelled. That is the value 3, the gas constant and the molar mass. These will get cancelled and you will have only the temperature, that is square root of T1 by T2. Now we have to find the new temperature T2. So squaring the above equation and rewriting this above equation for T2, we have T2 is equal to VRMS2 divided by VRMS1 the whole square into T1. We know the ratio of VRMS2 divided by VRMS1 as 3V by V. So substituting that value into 273, we get the value of T2 as 2457 Kelvin. The next problem. A gas is at temperature 80 degrees Celsius and pressure 5 into 10 power minus 10 Newton per meter square. What is the number of moles per meter cube if Boltzmann constant value is given as 1.38 into 10 power minus 23 joule per Kelvin? So they have asked to find the number of moles. So the given data is temperature T is given as 80 degrees Celsius, which you have to convert it into Kelvin by adding 273. So the answer is 353 Kelvin. The pressure of the gas is P is equal to 5 into 10 power minus 10 Newton per meter square. Boltzmann constant value is given as 1.38 into 10 power minus 23 joule per Kelvin. Volume is given as 1 meter cube. So we have to find the number of moles. We use our ideal gas equation, PV is equal to NKT. So reversing that equation for the number of molecules N, we get PV divided by KT. Substituting the values of P, V, K and T from the given data and simplifying, we get the N value as 1.02 into 10 power 11. So the next problem. From the kinetic theory of gases, show that moon cannot have an atmosphere. So K value is given as 1.38 into 10 power minus 3 joule per Kelvin and the temperature is given as 0 degrees Celsius, which is equal to 273 Kelvin. So once again writing the given data, we have T is equal to 273 Kelvin. Boltzmann constant is 1.38 into 10 power minus 23 joule per Kelvin. Mass of the hydrogen molecule is 3.33 into 10 power minus 27 kg. So first we are calculating the VRMS of the hydrogen molecule. Using the formula, V is equal to square root of 3 kT divided by M. Substituting the values, we get the VRMS of the hydrogen molecule present in the gas surrounding the moon is got as 1.84 into 10 power 3 meter per second. So the gas molecules are moving with this much great velocity from the moon. So it will not be there in the atmosphere of the moon. With this velocity, they will be moving away from the moon. So the moon doesn't have any atmosphere. Yeah, the next problem. If 10 power 20 oxygen molecules per second strike 4 centimeter square of a wall at an angle of 30 degree with the normal, when moving with the speed of 2 into 10 power 3 meter per second, find the pressure exerted on the wall. Mass of one atom value is given. So we have to find the mass of oxygen atom. So which is equal to 16, that is atomic mass into mass of one atom. So 16 into 10 power 20 into 2.67 into 10 power minus 26. The total mass is equal to 42.72 into 10 power minus 6 kg. Next, we will find the momentum of the oxygen molecule. Momentum, we know the formula as P is equal to M into V. M value now only we have found. V value, we know that it is 2 into 10 power 3, which is given in the data. So multiplying both, we get the momentum as P is equal to 85.44 into 10 power minus 3 kilogram meter per second. Now we will calculate the momentum normal to the wall at 30 degrees, which is equal to 85.44 into 10 power minus 3 into cos 30. So the answer will be 73.99 into 10 power minus 3 kilogram meter per second. We know the formula for pressure as pressure is equal to force by area. Force is equal to change in momentum. So now the change in momentum value we have found that 73.99. Substituting the change in momentum value and area value, we get 73.99 into 10 power minus 3 into 10 power 4 divided by 16, which is equal to 46.2 Newton per meter square. This is the value of pressure exerted on the wall. The next problem. During an adiabatic process, the pressure of a mixture of monoatomic and diatomic gases is found to be proportional to the cube of the temperature, and we are supposed to find the value of gamma, which is equal to Cp by Cv. So during the adiabatic process, we know the relation between T and P. The relation in an adiabatic process is T power gamma, P power 1 minus gamma is equal to constant. This is the equation for adiabatic process. Here it is given that the pressure is directly proportional to the cube of the temperature. So pressure is directly proportional to T cube. So T cube you take to the equation this side, it becomes T power minus 3. So here the equation becomes P into T power minus 3 is equal to constant. So the before equation we have P into T power gamma divided by 1 minus gamma is a constant. So in these two equations, in equation 1 and 2, the RHS is the same constant. So you can equate the LHS. So when you equate the LHS, you have P into T power gamma divided by 1 minus gamma is equal to P into T power minus 3. Now we are comparing the powers of T. So when you compare the powers of T, you get gamma divided by 1 minus gamma is equal to minus 3. Now moving this 1 minus gamma to the equation this side, you get gamma is equal to minus 3 plus 3 gamma. Simplifying this, you get 2 gamma is equal to 3 and gamma is equal to 3 by 2. So the value of gamma is found to be 3 by 2. The next problem. Calculate the mean free path of air molecules at STP. The diameter of nitrogen and oxygen is given as 3 into 10 power minus 10 meter. This is also once again a mere formula substitution problem. So the given data are the pressure value is equal to 1 atmosphere, which is equal to 1.01 into 10 power 5 Pascal. The Boltzmann constant value is 1.38 into 10 power minus 23 joule per Kelvin, and T is equal to 273 Kelvin. So first let us find the number of moles value using the ideal gas law. So N is equal to P by KT, substituting the P value, K value and T value and simplifying, we will get N as 2.68 into 10 power 25 molecules per meter cube. Now we have to substitute this value in the mean free path equation, which is lambda is equal to 1 by root 2 pi n d square. So once again substituting the values and simplifying, we get the lambda value as 9.3 into 10 power minus 8 meter. The next problem. A gas is made up of a mixture of 2 moles of oxygen and 4 moles of argon at a temperature T. Calculate the energy of gas in terms of RT. Neglect the vibrational modes. We know that for 2 moles of diatomic nitrogen with no vibrational mode, the energy is given by 2 into 5 by 2 RT. So 2 get cancelled and you will have the energy as 5 RT. For 4 mole of monoatomic argon, the value of energy is equal to 4 into 3 by 2 RT. So which is equal to 6 RT. So the total energy you have to add this 5 and 6, which is equal to 11 RT. The next problem. Estimate the total number of air molecules in a room of capacity 25 meter cube at a temperature of 27 degrees Celsius. So first this value of temperature we will convert it into Kelvin. So we have T as 300 Kelvin, Boltzmann constant as 1.38 into 10 power minus 23 joule per Kelvin, volume is given as 25 meter cube. Now using the relation PV is equal to nRT, which is equal to nkb nt. Using this equation we will find the value of number of moles as PV divided by kb into T. Now substituting the P value, V value, KB value and T value and simplifying, we get the total number of molecules in the room as 6.117 into 10 power 26 molecules.